You now have a toolkit: prompting, fine-tuning, RAG, CNNs for images, transformers for language. The question is no longer, can AI solve this, but which approach should I use? This question separates beginners from practitioners. Before building any AI system, you should ask three questions in order. Question one is, what type of input will your AI process? If you have images and video, that points to CNNs with transfer learning. If you have text and language, that points to LLM-based approaches. Structured tabular data often works better with traditional machine learning like XGBoost, while sequential decisions point to reinforcement learning. Question two is, what do you need to customize? If you need access to specific knowledge, like documents, FAQs, or databases the base LLM doesn't know, then use RAG. If you need to change behavior or style, meaning how the AI writes or responds, use prompting first, then fine-tuning if needed. Question three is, what resources do you have? If you have no data and need fast results, prompting is free and instant. If you have documents, RAG requires moderate infrastructure. If you have labeled examples, fine-tuning needs compute power. The approach must match your constraints. Here is a prompt to help you practice this decision-making. Ask an AI. I want to build an AI that helps Kazakh farmers identify crop diseases from photos. Walk me through the three questions. What's my input type? What customization do I need? What resources would I need? The golden rule is to start simple and add complexity only when needed. The progression is prompting, then RAG, then fine-tuning, and finally, custom models. Many problems that people think need fine-tuning actually just need better prompting. Now let's apply this framework to Kazakhstan's priority industries. AI Sana has identified 8 industries where AI can create significant impact. First is minerals and mining. Kazakhstan is the world's #1 uranium producer with major copper and coal deposits. AI opportunities include predictive maintenance using CNNs to analyze equipment images, safety monitoring with computer vision for PPE compliance, and ore grade prediction with ML models analyzing geological data. Second is food and agriculture. With 80 million hectares of farmland and major wheat exports, opportunities include crop disease detection using CNNs on smartphone photos, yield prediction combining satellite imagery with weather data, and precision agriculture with autonomous systems. Third is healthcare. Vast distances to specialists and rural access challenges create opportunities for medical imaging analysis with CNNs, patient triage chatbots, and AI-assisted telemedicine for remote consultations. Fourth is education. The trilingual policy and young population create demand for Kazakh language tutoring with fine-tuned LLMs, adaptive learning systems, and automated assessment tools. Fifth is fintech. Growing digital payments and underbanked rural regions need fraud detection using anomaly detection, credit scoring with alternative data for underbanked populations, and multilingual customer service chatbots. Here is a prompt to help you brainstorm. Ask an AI. Pick one AI Sana industry: mining, agriculture, healthcare, education, fintech, construction, telecom, or energy. Design an AI system for a specific problem in that industry. Which of the 3 questions helps you choose the right approach? There are also 4 cross-industry domains that apply across all 8 industries, multiplying opportunities. These are robotics and automation for process control, talent management for recruitment and training, media and marketing for content and personalization, and safety and security for anomaly detection and compliance. This creates a massive landscape of opportunity. 8 industries times 4 cross-domains equals 32 intersection points for AI ventures. For example, safety plus mining equals AI-powered mine safety monitoring. Talent management plus healthcare equals AI recruitment for rural doctors. The combinations are vast. The best AI engineers aren't those who know the most techniques. They're the ones who choose the right technique for each problem. Use the 3 questions, start simple, and match your approach to Kazakhstan's real needs. Now let's look at some concrete startup scenarios to see how these decisions play out in the real world. Case 1, misidentifying the input. Let's consider an agricultural AI startup called AgroVision KZ. In 2027, this startup, which was selected for AI Sana Cohort 3, set out to improve wheat yields in northern Kazakhstan. They identified that annual crop losses due to disease averaged 12 to 18%, representing a significant economic opportunity. The founding team consisted of a data scientist trained in Almaty, serving as CTO, and a former farmer from Kostanay, providing domain expertise. They faced a key decision challenge. The technical lead proposed using a multimodal large language model to analyze images and generate diagnoses. However, field research revealed that farmers primarily interacted through smartphone photos, often with limited connectivity and minimal text input. The core strategic question became, what type of input does the AI system actually need to process? Upon analysis, they realized the primary input was images of crops, meaning the task was visual pattern recognition. Since LLMs excel at language rather than visual classification, they made a strategic decision. The team adopted a CNN-based approach using transfer learning with MobileNet, while reserving LLMs only for explanation and user-facing communication. The outcome was impressive. They delivered an MVP in just 3 weeks and ran a successful pilot across 20 farms. This led to improved diagnostic accuracy and strong farmer adoption. The key takeaway here is that AI system design must begin with the nature of the input, not the popularity of the technology. Case 2, knowledge versus behavior. Next, let's look at avoiding unnecessary fine-tuning with an edtech scenario. Till AI, an education startup in the AI Sana education track, aimed to build a Kazakh language AI tutor aligned with national curriculum standards. Their initial assumptions favored fine-tuning a language model to achieve differentiation. They had to answer a strategic question. What exactly needs to be customized? Is it the AI's knowledge base or its communication style and behavior? Their analysis showed that the curriculum content resided in textbooks and exam materials, while the desired teacher-like tone could be controlled via prompting. Consequently, they decided to use RAG for curriculum knowledge and prompt engineering for instructional tone, deferring fine-tuning for later stages. The outcome was a government proof of concept approval and faster deployment with lower infrastructure costs. The lesson is to use RAG to extend knowledge and prompting to shape behavior, reserving fine-tuning for later. Case 3, designing within constraints. Now let's examine a rural fintech scenario called Nomad Credit. This startup targeted underbanked rural populations but lacked access to formal banking data, GPU infrastructure, and large labeled datasets. However, their available resources included mobile usage patterns, public demographic statistics, and survey-based behavioral data. They faced a strategic choice. Rather than forcing a deep learning solution, the team adopted gradient-boosted decision trees for credit scoring, using LLMs only for explanation and transparency. This decision resulted in a pilot with regional credit unions, competitive default prediction accuracy, and strong regulatory acceptance. The takeaway is that effective AI strategies align with available resources rather than idealized architectures. Case 4, ignoring the golden rule. Let's look at what happens when you start too complex with a healthcare AI scenario. Telemed Kazakh initially planned a fully fine-tuned medical LLM for rural telemedicine. After 5 months, they had no deployable MVP, were suffering budget overruns, and faced regulatory uncertainty. The team had to execute a strategic pivot. They reset their roadmap to focus on prompt-based symptom summarization and RAG for clinical guidelines, prioritizing data accumulation before any fine-tuning. The outcome was immediate. They launched a pilot within 1 month and secured hospital partnerships. This proves that AI systems should evolve incrementally, starting with prompting, moving to RAG, then fine-tuning, and finally custom models. Case 5, structuring innovation opportunities. Finally, let's look at the AI SANA Venture Framework. This framework identifies 8 priority industries such as mining, agriculture, healthcare, and education, alongside 4 cross-industry domains: robotics, talent, media and marketing, and safety. This creates 32 structured opportunity spaces. For example, combining mining and safety creates opportunities for computer vision in accident prevention. Combining healthcare and robotics could lead to elder care companion robots using LLMs, RAG, and reinforcement learning. The takeaway is that scalable AI venture ideation emerges from structured frameworks, not isolated inspiration. To conclude, the most successful AI practitioners are not those who master every technique, but those who consistently select the right technique for each problem. Strategic clarity about inputs, customization needs, and resource constraints is what transforms AI from a technical experiment into a sustainable business. Let's summarize the key takeaways. Always start by asking 3 questions: what input, what customization, and what resources. Remember that images require CNNs, text requires LLMs, and structured data requires traditional ML. Use RAG for knowledge access and prompting or fine-tuning for behavior change. Follow the golden rule of starting simple, prompting first, then RAG, then fine-tuning. We explored the 8 AI SANA industries, including mining, agriculture, healthcare, and education. And we looked at the 4 cross-domains like robotics and safety, creating 32 unique intersection points for new AI ventures.